HowIPWorks.com, the Internet Protocol, part of TCPIPWorks.com. HowIPWorks.com. In this section, we're going to talk about IP and how it relates to the OSI model and how it resides at the OSI model network layer. We'll talk about IP addressing, we'll talk about routing, and then we'll talk about IP routing mechanisms. We'll look at key fields in the IP packet formatting. We'll look at a detailed example of routing. Then we'll talk about packet fragmentation. Then we'll look at the time to life field in the IP packet, and finally the protocol ID field in the IP packet. OSI model, the network layer. Now, according to the OSI model, any protocol to be considered a network layer protocol must provide network-wide addressing and a mechanism to move packets between multiple networks. IP, or the Internet Protocol, is a network layer protocol because it does provide network addressing and it provides a mechanism for the movement of packets between different networks. This is a process that we call routing. The Internet Protocol, IP. Now, the Internet Protocol, or IP, is part of the TCP/IP suite of protocols. It is a network layer protocol according to the OSI model, and it's responsible for network addressing. This is our IP addresses and also the process of routing. It's covered and explained by numerous RFCs and certainly is part of the protocol standard that is required to get access on the internet. Network layer, network-wide addressing. Now, we really have two different addresses we have to be concerned about. When we talked about Ethernet and also when we talked about the data link layer, we talked about these things called MAC addresses. Now remember, a MAC address is a unique address burned to the network interface card by the manufacturer. And that address, sometimes called again the MAC address or the hardware address or the physical address, is the address that's placed in the Ethernet frame header and is used to transfer packets between devices on the same physical segment, also sometimes called the same subnet. Now, when we talk about network layer addressing or network addressing, these are addresses that are used network-wide. They are used to transfer data across physical segments or subnets, and really they are, in our example, the IP addresses used by routers to forward packets to different networks. IP addresses. Now, an IP address is a 32-bit binary number, and it's expressed as a series of 4 numbers, decimal numbers, separated by dots. An example is 206.77.105.9. Now, each device needs a unique IP address, at least one unique IP address. Routers and other specialized devices may have multiple IP addresses, but your standard workstation or computer would have a single IP address, and it must be unique. Now, IP addresses are configured in the TCP/IP software that comes with networking devices, and they can be manually typed in, or addresses can be automatically allocated to devices via something like a DHCP server. Not only do you have an IP address with each network device, but you will always have a subnet mask. In addition, you may, in most cases, will have a default gateway. IP addresses. Now, each TCP/IP device, or each host, or each computer needs a unique IP address, at least one unique IP address. If it has additional connections to the network, it will need a unique IP address for each connection to the network. It also will need a subnet mask. Now, a subnet mask is a number that accompanies the IP address and identifies which portion of the IP address is the network ID and which portion of the IP address is the host ID. The IP address and subnet mask are interrelated, and each only has meaning in the context of each other. The IP address and subnet mask are the minimum addressing requirement for any TCP device. If a device has an IP address and it has a subnet mask, it will be capable of local communications. This is communicating with any other host or device on its same physical segment. Now, if I want to configure my computer or host for remote communication, in most cases I will want to do that, I would need to enter in the address of the default gateway. Now, when I talk about remote communication, I'm saying that I want to connect to hosts that are on different physical segments than mine. So in order to do that, I would configure the default gateway. Now, the default gateway is the IP address of the router on my same physical segment. So once I've added the IP address and subnet mask, I have local communications. I can communicate to hosts on my same physical segment. And by adding the default gateway, the IP address of the router on my segment, then I'll have remote communication and be able to potentially communicate with everyone on the network. Routing. Now, routing is a process of intelligently moving packets from one network to another. Now, IP packets contain routing information, and routers are network layer devices that use the information in the IP packet to make routing decisions. Now, an example here, a packet comes to the router on the left. The router on the left examines the information in the IP packet to determine where to send that packet. It sends it to the middle router. Then again, the middle router, because it is a network layer device, has access to the network layer information inside the IP packet. It examines that information, in this case determines that the bottom router is where the packet needs to be forwarded to. Now you will note that in routing, the packet is only forwarded to a single router. Now this is very much different than what hubs or concentrators do in Ethernet. Now a hub or a concentrator in Ethernet is a non-intelligent device, because what a hub or concentrator does is it receives a packet and then sends it out on all ports. And that's very much different than a router, in which a router will send it only to the proper device. A hub or concentrator is considered a data link layer device because the hub or concentrator really only has access to the information in the data link layer header, which is the Ethernet header. In the case of a router, again, the router has access to network layer information, the network layer address specifically, and then it can make routing decisions based upon that network layer information. IP routing mechanisms. In this section, we'll take a look at IP routing mechanisms by first looking at the IP packet format and focusing in on specific fields within the IP packet format that are connected to routing. We'll take a look at an example of how routing works. We'll then talk about IP packet fragmentation. We'll also take a look at the IP packet life and time to live field. And then finally, we'll finish up with the protocol ID field. IP packet format key fields. At the bottom of the slide, we have a block diagram of a complete data frame or data packet. Now, the yellow part is the data, the green part is the IP header, and then the white blocks, the data link header and the data link CRC, represent the Ethernet headers. In the data is an upper layer protocol, upper layer from IP, and generally that would be TCP or UDP information. In this discussion, we want to focus in on a couple key fields that are listed here inside the IP header. Now, these are not all the fields that are in the IP header, but these are the important ones for our discussion about routing, and they are the source and destination IP address. So in each IP packet, there is the source IP, that's who is sending the packet, and then the destination IP address, who this packet is going to. There are also fragmentation related fields. These are the identification field, fragment flag fields, and fragment offset fields. There is a time to life field, and that's used to determine packet life, and then finally a protocol ID field. IP packet routing. Now, really to start this discussion, we should have a little background on what a segment or a subnet is. Now, generally, all devices or all computers within the same segment or subnet are interconnected by Ethernet hubs if you're using Ethernet. However, when networks get really large, traffic gets really heavy, or when you're trying to interconnect different networks that are geographically dispersed, what you will do is you will interconnect these different segments or subnets with devices called routers. Now, when a router initiates, when the power is turned on, the first thing they do is try to determine which networks they're connected to. Now, once they've determined this information, then the routers will exchange this information with other routers, and they use special routing protocols like the Router Information Protocol, RIP, the Cisco Protocol, IGRP, or BGP, and there's really actually a large number of different routing protocols. But based upon the information they discover when they start up and the information they receive from other routers, the router will build a table, a routing table, that gives them the information they need to forward packets to all the different networks. So when a router receives a packet, it looks inside the IP header information, it looks at the destination IP address of the packet, the address where that packet's destined to, it compares it to the router table, and from that it determines what the next router is that it will forward that packet to. And this process then is repeated at every router until it gets to the destination computer. IP routing example. Now, in our example here, we're going to have the computer in red with the IP address of 9.9.90.2 send a packet to 10.10.100.2, the blue computer in the right-hand corner. So what happens is that step one, the red computer creates an IP packet, and in that IP packet, it puts the destination address of the computer it's going to, that's the 10.10.100.2, and then of course it puts in its own source address. Now, the computer in red will then take that packet and send it to the router. The router, when it receives that packet, will look in the IP address information, see that that packet is destined for the computer 10.10.100.2, and it will look in its router table. Now remember, when routers come up, what they do is they look at all the networks they're connected to, they exchange information with other routers, and they create these things called route tables. And by looking at this route table, router 1 will see that it has to forward the packet destined to the blue computer to router 2, because that's where that computer resides. So the router 1 will take that packet from the red computer and then forward it to router 2. Then when router 2 receives the packet, it will then look at that packet, look at the IP information. It will look at the destination IP address at 10.10.100.2. It will compare that against its route table and see that that computer is on its local segment. From there, router 2 will then forward the packet or route the packet to the destination computer. Routing may involve going through just a single router. For instance, if the red computer wanted to send a packet to the gray computer 20.20.200.7, it would only go through one router. But routing also may involve going through two or more routers. In fact, on the internet, routing sometimes involves going through a dozen or more routers to get to the destination station. IP packet fragmentation. Now, there are situations in which a single IP packet can be subdivided by a router into multiple packets during data transmission. To understand why this happens, let's talk about maximum packet size. Now, the maximum size of a complete packet or data frame is determined by the data link layer. This would be Ethernet or token ring. And there could be a situation where a packet could start on a network with a large packet size and then travel over an intermediate network that has a smaller packet size. And this would be a situation where one of the intermediate routers would then have to fragment or chop that packet into smaller pieces to accommodate the intermediate network. Now, the one thing about packet fragmentation is that it is undesirable, considered undesirable, because it slows data transfer. Because we have a situation where a router needs to take the time to divide a packet, then transfer it, and then the receiving station has to take that packet that's been fragmented and reassemble it, and that all takes time. Why fragmentation occurs? Now, in this example, we have two different networks interconnected by a router. Now remember, the maximum packet size or frame size is determined by the data link layer protocol. Now, an Ethernet packet, by specification, can be a maximum of about 1.5K. In the case of token ring, it can be 4K or bigger, but we're going to say in this case our token ring network has a maximum packet size of 4K. Now, when Ethernet wants to send a packet, or an Ethernet station wants to send a packet to a token ring station, that's really no problem, because we have a 1500 byte packet that's sent to the router, and the router can easily transfer that into a token ring packet whose maximum size is 4K and then pass it on to the station. The problem arises when there is a station on the token ring side that wants to send data to an Ethernet station, because in this situation, a token ring station may very well create a packet that's 4K in size. It would get to the router. The router would say, gee, I have a packet that's 4K, but I have to send it on Ethernet, and that will only accommodate 1.5K. So at this point in time, the router would then have to divide or fragment that packet into at least 3 pieces, and then send each fragment as a separate IP packet to the destination computer on the Ethernet segment. Then the Ethernet station would take the 3 IP packets, the 3 fragments, and then recombine them into the original IP packet that was sent out by the token ring station. How IP fragmentation works. Now, in our situation, we've got a router that has to divide or fragment an IP packet. Now remember, the contents of an IP packet are probably an upper layer protocol like TCP or UDP, and then the data it carries. So the router will take the contents of the IP packet and then subdivide it into multiple fragments. Let's say in this case 3 fragments. Then it will need to add an IP header to each of the fragment before it forwards it on. But what it's going to do is use information inside the IP header to identify the fragments so that the destination computer can recombine these fragments into the original IP address. Well, what it's going to do with each fragment is add the same number to the identifier field in the IP packet of all the fragments. Because what's going to happen is that a IP station may receive lots of different packets, and what it needs to do is recombine in this case, the 3 fragments into a single packet, and all 3 fragments will have this same identifier number that no other IP packets will have, and then that way the destination computer will be able to associate these 3 fragments as being part of the same original packet. But what it's going to also do is add an incrementing number to the IP header field called fragment offset. So the first fragment would have the offset number 1, second fragment would have the offset number 2, third fragment might have the offset number 3, because again, what could happen is that the IP destination computer could be receiving a lot of different IP addresses, a lot of different IP packets. It will first identify all the fragments as being part of the original packet because they have the same identifier field, and then it will be able to arrange them in the proper order by looking at the offset. The first offset packet is 1, second 2 is 3, it'll put them in order and then be able to recombine that packet. Now lastly, before the sending computer sends out these fragmented packets, it will add a flag to the fragmentation field. Now again, this is of the IP header, to all but to the last fragment packet, because there has to be a way for the destination computer to know it has all the fragments and that it will then be able to recombine them. So the first packet will have the flag, second packet will have the flag, again indicating there's more coming, but when it gets to the third packet, it will see that, oh, there's no fragmentation flag. This will be the last fragment. Then I'll check the offsets to make sure I have all the different numbers, and then finally recombine the fragments into the original packet. IP packet life, time to live, or the TTL. Now, there must be a way to prevent packets from endlessly looping or being routed around a network. There could be situations that if routers are improperly configured, that packets endlessly circle around a network, never getting to their destination. Well, there is a special field inside the IP packet header to help prevent this problem. This is called the time to live field. Now, when a packet leaves a computer, the time to live field in the IP packet header is set to, by specification, a maximum of 256. In the case of Windows NT, I believe it was set to 128. But when the packet is transferred to a router, to any router, each router will decrease the time to live by a value of 1 or more, depending upon how the router is set or if there's congestion. So as the packet travels to the network, the time to live decreases each time it passes through a router. If the packet reaches a router, the router decreases the time to live, and the time to live reaches 0, then the router will send the source computer, the computer sending this packet, a special packet called an ICPM, time exceeded, and it will discard this packet. It'll throw the packet away, it won't be routed anymore, and it will notify the source computer that the destination is unreachable and don't send any more packets. IP protocol ID field. Now, IP can carry a number of different upper layer protocols. Inside an IP packet could be a UDP packet, it could be a TCP packet, it could be an ICPM packet, it could be a lot of different types of packet. Well, the protocol ID field inside the IP header is a number that tells IP what type of data is inside it. Now, for instance, if an IP packet had a protocol ID field of 6, that means that the contents of the IP packet was a TCP packet. If the protocol ID field was 17, then that would tell IP that the contents of the packet is a UDP packet. So when the IP program receives an IP packet, it looks in the protocol ID field. If the protocol ID field tells it's a TCP packet, it takes the contents of the IP packet, gives it the TCP program for continued processing. If the protocol ID field tells it's a UDP packet, then it would give the contents of the IP packet to UDP for continued processing. Now you will note that this is very much like the Ethernet type field, because in the Ethernet type field there is a number that indicates the content of the Ethernet packet. Now remember, if the Ethernet type field is 0800, that indicates to Ethernet that the contents of the Ethernet packet is an IP packet and would pass it off to IP for continued processing. Then when IP looks at the protocol ID field, for instance, it might see that, oh, the contents of the IP packet is TCP, and so it would know to hand the contents of the IP packet to TCP for continued processing. Now we will see in the TCP section that TCP has a port that identifies what the contents of the TCP packet is, so that TCP can then hand the contents of the TCP packet to the next upper layer protocol for continued processing. The Internet Protocol, IP. Now, the Internet Protocol, or IP, is part of the TCP/IP suite of protocols. It is a network layer protocol according to the OSI model, and it's responsible for network addressing. This is our IP addresses, and also the process of routing. It's covered and explained by numerous RFCs, and certainly is part of the protocol standard that is required to get access on the internet.